So try to estimate the differences. We have to assume certain model. Then we'll start with the Jukes and Cantor's model. That's the one parameter model, showing this diagram, which is very simple. We have 4 different nucleotide states, A, T, G, and C. For any given nucleotide, if a mutation occurs, there are 3 different states they can change to. So for example, A can change to T, C, or G, right? So if they change to an alternative nucleotide, then we say that's a mutation. And the parameter we are assuming here is the equal probability for any different state. So for a given A to T, or A to C, or A to G, they have equal probability to change, then we call that alpha, showing in the figure on the slide. So you can see the arrows points to the mutation, the direction of the mutations, then the alpha on each line showing the probability. So although you know this is not entirely true, but we will start with this simple model to estimate the substitution rate. So let's start with the A, like nucleotide. So if we start with an A nucleotide, there are several possibilities. The possibility is the A can stay as an A nucleotide after a certain time period. Or the A can change to T, or G, or C. If A changes to T, the probability is alpha. If an A changes to G, the probability is another alpha. If A changes to C, then the probability is still alpha. So there are 3 ways to make the change, right? Then you add it in together. So that's 3 alpha. And what's the probability for a nucleotide starting with an A without any mutation ended with an A? That means the nucleotide didn't change to T, G, or C. And that's the one we calculate here. So we want to show if we start a nucleotide A at a time equal to 0, then what's the probability at time equal to 1, the nucleotide is still an A status. And that's showing in this formula, that's the probability P, A, in parentheses 1. 1 means the T equal to 1. So we're from T equal to 0 to T equal to 1. And that's the probability is 1 minus 3 alpha. Because alpha is the probability they change, right? But then there are 3 different ways they can change to an alternative nucleotide. And the probability they don't change, they stay with A, that's 1 minus 3 alpha. So that's a very simple one. Then we want to know what's the probability if given another time unit, 2, T equals to 2, and still it's an A. So I want to show that at the bottom of the slide, there are 2 paths. Because you are concerning at the time T equal to 0 is A, and given 2 units of time, now it's the T equal to 2 is still an A. Okay, there are 2 possibilities. One is on the top, it's A for all the time points. So it's A at T equal to 0, T equal to 1, T equal to 2. And there's an alternative path is at T equal to 1. There's a mutation happen. It's either changed to T, G, or C. Then it changes back. So there's a reverse mutation. It changes back to A at the time equal to 2. So if you understand or you can divide the two possibilities. Then you can calculate what is the probability for a given nucleotide site stay with A at T equals to 2. So that's the formula showing on the top of the slides in blue. So at T equal to 2, the probability this nucleotide still at A status is equal to the first pass. They always the same. Or the second pass, they change to a different nucleotide. So it's still stays the same. It's the 1 minus 3 alpha, right? We just mentioned in the previous slide. But remember, it's from T1 to T2. So look at the second part of the formula. It's so 1 minus 3 alpha, that's the probability A didn't change. And times P at time equal to 1 is an A. So that's the part before the plus. And the second part is if they change to a different state, T equals to 1, at time equals to 1. And that means the second pass, it's a non-A state. Then what's the probability from a non-A state to an A? That's alpha, right? That's the probability they change from a non-A state to A. It doesn't matter if it's a T or G or C, because the probability is always the same. It's alpha, because the final state is an A. So that's the second part of the formula. So it means the first at T equal to 1, the nucleotide is a non-A. So its non-A is 1 minus the probability it is an A. And times the proportion, the probability change back to A, that's alpha. So that's the second part of the formula. Alpha times 1 minus PA1. So that's what we are calculating. At time 2, like time equals to 2, then what's the probability the nucleotide still stay with an A? So that's the calculation for the probability. Then you know we have to go back to P0. So we can look at the formula, and this is what we learned in high school. So we substitute the 2 to T plus 1. Then you know the 1 becomes T. So we can change the formula on the top to the one in the middle to get any given time. The probability is stay with the same nucleotide. It's the formula based on what's the status in the previous time point. Here is the time equal to T. So we just change 2 and 1 to T plus 1 and T in the formula. The formula are exactly the same. Then you can calculate the formula based on, because every time you make a change, it's based on what's the previous state, right? So if you're concerning T plus 1, you ask what's T. Then if you're concerning T and what's T minus 1, and you go back step by step. Then you can calculate the delta P. Delta P is, we can estimate amount of change per given time or per unit time. So it's like time equal to 2 to time equal to 1. And what's the differences? And that's the delta P. And you can get the simple calculation for delta P based on just arrange the formula. Then we can calculate a little bit more about any given time. You don't have to memorize the formula, but just tell you a little bit about if you trace back to time 0, and since we already assume for any given nucleotide or any site, our starting point is A. So that is a given. So when I give that assumption or that status, that means the probability that nucleotide is A is 1, because I already told you. There's no alternatives. So that's where we start with. So the P at equal to 1, the probability of this site at time 0 as an A is a given. So that's 1. So this is something you have to bear in mind. And if we put them then all together, we can calculate the time t point, any given time t, the probability of a site to stay with an A, and what's the formula? Then that's the one given in the bottom of the slide. Okay, so this one just tell you there's an alternative way to write this. So then they are all the same. So this is to say, for any given sequence, the two status, the two sequences are exactly the same. Then that's, we say A, or some people use AA, means the two are exactly the same, both are at the A status, or use II to generalize any given nucleotide. So these three are just different expressions for the same formula. And the later on is all the same because we only concern about the alpha is the probability of the change. So there's only one parameter here. So the Jukes and Canton's method also count as a one parameter method. Okay, so given this formula, then we will talk about when it's not A, right? Because we say we start with the A nucleotide. But how about if it's not it's a non-A state and change to A? So there are only two possible. The truth is, now you look at the sequence, they are A at the current time. So at the time t, both of them are A. So that's the truth, that's the observation. And you want to ask what happened in the past. There are two possibilities, and we already talked about one possibility is we start with the nucleotide is A. Then at the final status, they are A again. And what's happening in the middle? Their second possibility is they start with the non-A state. Then at the end, it's an A. So there are just two possibilities. And here is just given when it's non-A at the time 0. And the probability here is 0. And you can calculate what's happening after period of time. So that's the formula showing in this slide. Then of course you can more case is like, okay, let's talk about if it's from G to A, and that's showing on the second part. From a G status to an A status. So this is the same thing. That's a different expression for the same formula here. Or you want to write IJ, means it starts with one allele I and change to a different allele J. So that's like talk about the same, like a very similar expression, but using the different notation. But the formula are exactly the same. So this part of the formula is talk about from an I state to a J state and what happening in the middle. We want to estimate all the different substitutions during the time t. And this just try to illustrate all the probabilities. Maybe we should go back to the previous slide. So this one you can see at the end, you will see that's a quarter, so 1/4. A quarter minus a quarter of the e to the power of minus 4 alpha t. So alpha is the change from one state to the other. That's the parameter we assume in this model. T is the time, right? So these two contribute to this formula. If given the time, so if the time is very, very long, so assume T is extremely large. Then in that case, the second part will be very, very small. to approximately to 0. And this formula, if we given the time to the infinity, then this formula will give you an answer saying the probability will become a quarter, that's 0.25. And if you understand that part, you will know for any given two sequences, even unrelated, you will find 25% of the similarity at the DNA sequence level. That is the same as for any given sequence you evolve for a time to infinity, then the changes will randomly accumulate. And if you at the end point, you compare the two sequences, they will be very diverged. And the similarity between the two will only for like 0.25.